All right, howdy everyone. This problem has to do with an epoxide reaction carried out under acidic conditions as shown here. I would consider this to be a arrow pushing mechanism of moderate complexity for those of you studying typically topics such as ethers, alcohols, and epoxides. Often those are lumped together in the same chapter. Epoxides are kind of a very special form of ethers, as many of us know. And what makes them special is that they're kind of spring-loaded to open via a number of different mechanisms. And often the conditions used to open up that epoxide help dictate what kind of product you get from the epoxide opening. As I try to do with all of our arrow pushing mechanisms, the first thing I try to do is compare the starting material to the product and identify some of the bonds that are being made and broken. Often that's easiest to do if you label carbons in your starting materials. And so here I'm going to label the carbon 1, 2, 3, 4, 5, 6. And if I follow that in the product here, then I have 1, 2, 3, 4, 5, 6. And then the remaining carbon must be 7, and that must be the 7. And that really helps out because now we can look at what bonds are made and broken. And we can see at carbon 5, there is a carbon-oxygen bond in this epoxide that needs to get broken. And the carbon 5-7 bond here needs to be formed. Additionally, the 2,7 pi bond is broken, but there is a hydroxyl now at the 2 position. And so this really helps us map out what sorts of reactions need to occur. And clearly by doing this, we can see that both the epoxide, which is opened in the product, as well as the alkene need to participate in the reaction. Now, the next thing I like to do is to identify what kind of reagent I have. And here we're given sulfuric acid as the reagent and water. And so before we get too carried away there, one thing I like to remind myself is that in water, sulfuric acid generates H3O plus and then HSO4 minus. And so if we're going to be using acid here, we should be using H3O plus as our proton source. Okay, like I do for all of these, this is the point where I encourage you to click pause, try this mechanism all on your own, and then come back after you have a good guess as to what the problem is. Ideally, it'll be solved, and you'll just be checking your answer by watching the rest of me. So ready? Go ahead and click pause right now. Okay. Hopefully now that you're coming back, you're coming back to look at the answer to this mechanism. Because we talked about H3O plus being the acid, I'm just going to draw that out. Now, there are really two places in this molecule that we could protonate, and that would be the alkene or the epoxide. And so let's just consider very briefly both of them. So I'm going to take the red arrow here for my oxygen lone pairs, and I'm going to have those do the protonation. And so this is a reasonable intermediate to start from. The other intermediate that we could imagine, I'm going to get to with the green arrow here, and that would be using the alkene as the base and protonating it to make a carbocation. Now, there's really nothing wrong with protonating the carbocation with sulfuric acid and water. That's a reaction that hopefully we've seen before. What is special here is that that's not really going to get us to the product. And so we could imagine a byproduct of this reaction being the attack of water onto that tertiary carbocation. And then we could imagine more water deprotonating that protonated product, and then this would generate some more H3O plus that could go on and do more chemistry. And this then would be the hydrated starting material. This is perfectly reasonable as a product, but it's not the product that we're actually asked to draw. And so if you took the detour of protonating the alkene, I would say that that's totally reasonable. It just doesn't help you solve this problem. And often you'll find out that some of these problems are solved starting from one particular place and going forward. Sometimes they're solved going backwards to the starting material from the product. And sometimes you draw things out that are quite reasonable. They just don't get you where you're going. And so I would classify the hydration of the alkene in this particular example, the information I've drawn in green, as something that's reasonable, but it doesn't quite get you to the product. For those of you that want to think about it more critically, the protonated epoxide should be, similar to H3O plus in terms of its acidity. And whereas usually carbocations we think about as being a little bit higher energy intermediate. And so maybe it's sensible that you protonate the epoxide first over the alkene. To put that a different way, I think if we looked at the pKa's, we would imagine that the ether would be a more basic group than the alkene. Okay, so it turns out this is going to be the correct pathway here to get us to the product. And so I'm just going to continue with that arrow pushing mechanism. Protonated epoxides now are really good electrophiles. And there's a couple of things that they could do, one of which is to be attacked by the alkene. And remember, epoxides that are protonated tend to react at the more substituted position instead of the less substituted position. So less substituted on this side, more substituted on that side. And so we would expect the addition to go under acidic conditions to the more substituted side, the secondary side in this substrate. Okay, so now we would generate our carbocation in a 5-membered ring. If I count, it should be 1, 2, 3, 1, 2, 3, 4, 5. So we get a 5-membered ring out of that. Then we would have our alcohol dangling off, our methyl group down, and now we have a carbocation at that site. So for those of you that started with this green mechanism or the alkene hydration, all of that effort you put in wasn't necessarily wasted effort, because those same steps up here that were the incorrect answer, now we're going to be able to incorporate into the correct answer, because now we have a tertiary carbocation just like we had up here, and now we're going to be able to attack that with some of the water that's floating around in the exact same mechanistic steps. And now again, for the last step of this process, we're going to again use some more water to do the deprotonation to generate some more H3O plus. Getting kind of an ugly arrow here. And then this will generate our product. And so that's all good. And it totally should flow from there. One thing that I will point out is that I try to use the H3O plus as both the acidic group, because sulfuric acid should protonate that water first, but I also use water as the base because water has to be, by definition, more basic than the sulfate anion. And so that is something that I think is important to highlight, is that water here is both the nucleophile, but then also the base in the next step. I want to take one last second here to point out another potential complication of this reaction, and that goes back then to this intermediate. So here we had water attack at, or I'm sorry, we had the alkene attack at the more substituted side, and that's okay. We could also imagine, by the way, having water open up the same epoxide. And if I draw the protonated epoxide here again, I could imagine my same water nucleophile coming in and doing that attack, and then that would generate this intermediate, and again, I could have water deprotonate that intermediate to ultimately generate a diol. Now, some of you might ask, okay, at this stage, I've said that there's a green pathway that we could imagine. There's the desired black pathway that leads us to the product that we're given. And then there's this extra pathway where water does the hydrolysis. And so now we've talked through 3 different possible pathways for this acid catalyzed opening of the epoxide. And I say acid catalyzed, by the way, because you'll notice in all these mechanisms, H3O plus comes back out of the reaction. And so we start with H3O plus promoting the reaction, and then in all cases, we form H3O plus. And so strictly speaking, it's acid catalyzed. But we have 3 pathways, and so the question partially boils down to how do you address that? It makes it much more complicated. One thing I would say is for arrow pushing mechanisms of this sort, you're not necessarily as a student responsible for all of the possible outcomes. Typically, the expectation is just to draw a pathway from the starting material that you're given to the product that you're given, and the other possibilities aren't necessarily part of the question. That might be satisfying to those of you that are looking for a good grade, but for those of you that are looking to genuinely understand organic chemistry, that's obviously not a very satisfying answer. To those of you that are really looking for the kind of real answer or the true answer, if you will, what I would say is in the lab, we often experience byproducts for these reactions. And so the overwhelming majority of the chemical reactions that we actually run experimentally in organic chemistry have well below 100% yield. And often that yield is low because we have byproducts. And often these arrow pushing mechanisms help us identify what some of those byproducts could be, and they let us expect potentially ways to troubleshoot around them. And so this is an example where the desired product might be the dominant one, but you'll notice we're not given a yield here. And so it's hard to know if the yield is 99% or if it's 60%. And it's quite possible that it's a good yield, but that these other byproducts that we're talking about do pop up or do appear in experimental conditions. And so that's what I would say to that. Okay, so that concludes this arrow pushing mechanism. Again, I would consider this one to be of modest difficulty for those of you studying epoxides and ethers. Please, if you're enjoying these videos, do subscribe to Professor Carbon on YouTube. Also, feel free to reach out to us on social media, leave us some comments, and if you're really enjoying these videos and you want access to the PDF notes, please do subscribe to us as a patron. We really would appreciate that. All right, thank you.